What specific problem does the Kolmogorov-Arnold Transformer, CAT, aim to solve in the context of enhancing vision transformers, and why is it significant to address this issue?
The Kolmogorov-Arnold Transformer, CAT, aims to solve the scalability issues associated with integrating Kolmogorov-Arnold Networks, KANs, into vision transformers, VITs. Specifically, CAT addresses three major challenges: the inefficiency of B-spline base functions in parallel computing environments, the exponential growth of parameters due to unique input-output pairs in KANs, and the inadequacy of weight initialization that leads to instability during training. By introducing innovations such as rational activation functions, parameter sharing through group CON, and variance-preserving weight initialization, CAT enhances computational efficiency and model stability. This is significant because it allows CAT to outperform traditional MLP-based transformers while maintaining comparable computational requirements, thereby improving the expressiveness and efficiency of transformers in large-scale applications like image recognition and object detection. Ultimately, addressing these issues enables CAT to leverage the theoretical advantages of KANs effectively, making it a competitive alternative in deep learning architectures.
Can you explain in detail how the Kolmogorov-Arnold Transformer, CAT, integrates CON layers into the transformer architecture? Illustrate the step-by-step process of its design and functionality.
The Kolmogorov-Arnold Transformer, CAT, integrates Kolmogorov-Arnold Networks, KANs, into the transformer architecture by replacing the traditional multi-layer perceptron, MLP layers with CON layers, specifically utilizing a novel variant called Group Rational CON, GR-CON. The design process begins with flattening a 2D image input into a 1D sequence, followed by applying patch embedding and positional encoding. In each CAT layer, the CON layers are employed in place of the MLPs, where the GR-CON utilizes rational functions as base functions, enhancing computational efficiency and expressiveness. To address scalability issues, CAT implements three key innovations. 1. Rational activation functions that are optimized for GPU performance. 2. A group CON approach that shares parameters among groups of edges to reduce computational load. And 3. A variance-preserving weight initialization strategy to ensure stable training. This integration allows CAT to maintain the attention layers of the original transformer while enhancing the overall model's performance, as demonstrated by its superior accuracy on tasks like ImageNet classification compared to traditional MLP-based transformers.
Could you provide an illustrative example demonstrating the inner workings of the Group Rational CON, GR-CON, within the CAT? Walk through the operations with specific inputs and outputs to clarify the concepts.
The Group Rational CON, GR-CON, operates by sharing parameters among groups of input channels, which enhances computational efficiency. For instance, consider an input vector, x, with dimensions d_n equals 8 and d_out equals 4. If we divide the input channels into g equals 2 groups, each group will contain d_g equals 4 channels. The GR-CON will apply a shared rational function, f, to each group where the function is parameterized by coefficients a_m and b_n. For a specific input, x equals x_1, x_2, x_3, x_4, x_5, x_6, x_7, x_8, the GR-CON computes the output, y_j, for each output channel, j, as follows. y_j equals sum_i equals 1 caret d_in w_ij, fx_i plus b_j. Here, w_ij are the weights for the connections from input to output, and b_j is the bias for output, j. By sharing the parameters of the rational function across the two groups, the GR-CON reduces the number of unique functions needed from 8, 1 for each input-output pair, to just 2, 1 for each group, significantly lowering both the parameter count and computational demands. This design allows the GR-CON to efficiently process the input while maintaining the expressiveness of the model, ultimately leading to improved performance in tasks like image recognition.
What are the theoretical advantages of using rational functions as opposed to B-spline functions for the CON layers in CAT, particularly regarding their impact on computational efficiency and expressiveness?
The theoretical advantages of using rational functions over B-spline functions in the CON layers of the Kolmogorov-Arnold Transformer, CAT, primarily revolve around computational efficiency and expressiveness. First, rational functions are more suitable for parallel computing, as they involve simpler operations that can be efficiently executed on modern GPUs, unlike B-splines, which require recursive computations that hinder performance. Second, rational functions can approximate a broader range of functions, including those with singularities or sharp variations, more effectively than B-splines, enhancing the model's expressiveness. Additionally, the implementation of rational functions can be optimized using techniques like Horner's method, which reduces computational complexity during evaluation. Overall, these factors contribute to a more efficient and expressive architecture in CAT compared to traditional KANs utilizing B-splines.
How did you validate the effectiveness of the CAT model? Discuss the experimental design, the datasets used, and the metrics you employed to assess performance, as well as how these validate the proposed method's improvements.
The effectiveness of the Kolmogorov-Arnold Transformer, CAT, model was validated through extensive empirical experiments across various vision tasks, including image recognition, object detection, and semantic segmentation. Specifically, the model was tested on the ImageNet-1K dataset, where CAT-B achieved an accuracy of 82.3%, surpassing the performance of the Vision Transformer VIT model of the same size by 3.1%. Additionally, when initialized with pre-trained weights from VIT, CAT's performance further improved to 82.7%. The experimental design involved a direct comparison of CAT with traditional MLP-based transformers, focusing on metrics such as accuracy to assess performance improvements. These results demonstrate that CAT not only matches but exceeds the performance of existing models while maintaining comparable computational requirements, thereby validating the proposed enhancements in expressiveness and efficiency.
What limitations or challenges does the CAT encounter in scaling and integrating KANs, and what suggestions do you have for future research to address these challenges?
The Kolmogorov-Arnold Transformer, CAT, encounters several limitations in scaling and integrating Kolmogorov-Arnold networks, KANs. Firstly, the standard B-spline functions used in KANs are not optimized for parallel computing on GPUs, leading to inefficiencies in computation, C1. Secondly, KANs require a unique set of parameters for each input-output pair, resulting in an exponential increase in parameters and computational overhead as the network scales, C2. Lastly, the weight initialization strategy in KANs does not preserve variance effectively, which can lead to instability during training, C3. Future research could focus on developing more GPU-friendly base functions, optimizing parameter sharing strategies further, and refining weight initialization techniques to enhance stability and performance in large-scale applications.